Hi, I thought I would record a video for my students. It's going to be all about the monostable timer, also known as the one-shot timer, using the 555 timer IC. Now, when in normal lessons we talk about using this, we keep things very straightforward. We just say that we can have a switch here, which when pressed, then starts a timer interval, and then the output goes on high for a certain period of time. And that period of time is you can calculate it as 1.1 times R here times C. Okay, so typical lesson, we just keep things simple like that. However, every year when a student actually wants to use this circuit, we might have a little bit of a problem because say if you have a short time on for your output here, and the trigger is, the pin 2 is the trigger is kept low for longer than the time high for the output, then something a little bit unexpected for students typically happens. Okay, so we're going to have a look at that now. And then it's not too difficult to fix, but if you're a GCSE student, you're probably going to need to concentrate a little bit. Maybe if you're an A-level student, some of this you might pick up on a little bit more easily because we have considered the use of capacitors more in circuits than GCSE. So anyway, let's just have a quick look then. So by the way, I'm using, if you're not familiar with this software, I'm using something called Circuit Wizard. And at the moment, I've got a probe on the output, pin 3 on the output. And what I'm going to do is I'm just going to briefly, very briefly, just press that switch. I've also associated the keyboard key A, so if I want, I can just press A on the keyboard. But let's just quickly click that for a moment. And you'll notice that the output goes logic high. Remember, that's the red probe there, so we've got the red trace on here. The output goes logic high for about 1.1 seconds. Okay, that's what I would expect. Let's just try that again. So if I just press, and so very, very short duration press, remember, and so 1.1 seconds. Okay, so that's as you would expect. That's what we tell you in the lessons. Now, let's now press the switch, but then keep the switch depressed, like so, and you'll notice now that the output, if you look at the red trace on the graph, the output remains high and the LED remains on. Okay, so although we triggered the timing interval, we've somehow overridden it, so now it's staying on, and then when I release the key, you'll see there that the output goes low. So if you've got a long timing interval, and you can expect your user just to press the switch for a brief period of time or shorter than timing interval, then you don't have a problem. But when you've got a short timing interval, when you only want something pulsed very quickly, then this circuit can be a problem. So for example, let me just, let's say we'll reduce this capacitor to say 100 microfarads. And then I'm just going to, this time around, I'm going to press A on the keyboard because I can hit it and release it more quickly. I will do it in a moment. Okay. There. Okay. Now, is that duration actually controlled by how long I had my had the key pressed? Let's just press it there. That's now being controlled because I've got the key pressed. Or is it the timing interval? So I'll see if I can press and release the A key on my keyboard as quickly as I possibly can. And is that because that's the duration which I kept the key pressed? It's really difficult to know. Okay, so when you want to have a really short timing interval, this is not an adequate circuit. Okay, so what we'll have a look at now, I've got an improved circuit, and it definitely is going to work, but we need to just consider a little bit more about how the circuit works. So what do we got here? Pin 2. Pin 2 is the trigger, and the timing interval starts when the trigger, pin 2, is taken to 1/3 or less of the supply voltage. So conveniently, I've chosen 9 volts here. So 1/3 of 9 volts is 3 volts. So when pin 2 dips below 3 volts, then the timing interval starts. Let me just increase this, and I think I'll go for something bigger this time, 4,700 microfarads. So a nice long or longer timing interval, and let's just press that. And you'll see now that we've got our time on. Yeah, it's quite long, it's much longer than I pressed the key. Okay, now let's just move this here, and when I press the key, you'll notice that for the duration at which it's pressed, it takes it to a logic low, which is hopefully what you would expect because we've got a pull-up resistor, which means that normally pin 2 is pulled up to the supply voltage, 9 volts, and then when I press that switch, then we have the full drop in the source or the supply voltage across that resistor. And so effectively this point is directly connected to 0 volts, so that goes down to 0. If you'd like to see that in another way, I think I've got an even simpler circuit here, which is basically the same thing. Okay, so as you hopefully can see, and in fact what I'll do, I'll just take a screenshot of this and then I can annotate it. Right, okay, let's go for this program, and this is a freebie, by the way. Actually, I find it quite a decent program. So let's see that we got 9 volts there, and hopefully you can see that effectively that 9 volts is connected through there. Okay, and so because there is no flow of current, with no flow of current, because remember we say that voltage equals IR, okay, with no flow of current. So when the current I is 0, so 0 times resistance is 0, so there's no voltage difference between these 2 points. In other words, there's no voltage drop across that resistor. So if it is 9 volts here, it's still 9 volts here, so it is still 9 volts here. So hopefully that makes sense. But as soon as you actually have the flow of current, in other words, let's just change that to red. So as soon as you have the flow of current, because the switch is closed, then you will have current. You obviously have resistance in the resistor, and then so you have a voltage drop of 9 volts. Okay, so hopefully you're keeping up with this so far. So what we want to do then, let's just go back to the problem. We want to make the drop in the voltage to drop below 1/3 of the supply voltage, but we want it to only be a momentary drop. We want it to be independent of how long the user actually presses that switch. Okay. I think I've got another thing that might possibly be useful here. In fact, before we go for that one, let's just have a look at the this here. Okay. So let's just run the simulation. Now this is showing from when I previously run it, so just ignore that for the moment. And when I run this simulation, you'll notice that the voltage of the capacitor, because that's what I'm probing now, the voltage of the capacitor rises until it reaches the supply voltage. And once it is fully charged, as good as fully charged anyway, because the capacitor in theory charges it just keeps on charging infinitely, but at a lower and lower rate. But when it's fully charged, effectively there's not going to be any flow of current. It acts as an open circuit, and in other words, you can probably see that that is what the symbol is representing. It's representing two plates that are separated by a dielectric, by a space, and so you won't actually have any current flow across them. So it charges up. All right. Now it's important to understand that once it is charged, let's just zoom out a little bit. Once it is charged, it has charged to the 9 volts. Okay, so that is important to understand, that it charges up to the supply voltage. Let's just go to this thing now. Okay, now what I would like to do is take another screenshot of this. Hopefully you're finding this useful. By the way, if you do find it useful, please do like and subscribe if you want. Okay, so yeah, it helps me out a little bit. And so let's just put this here. And the reason why I was showing you this earlier, okay, sorry, not that one, showing you the capacitor, because actually, hopefully you're going to see that this resistor and capacitor actually features in this circuit, okay, because when you actually look at it, you've got this resistor and this capacitor, which when this switch is closed is effectively just the resistor and capacitor, just like the resistor and capacitor there. It goes from the supply, resistor, capacitor, ground, and then goes from the supply, resistor, capacitor, and if the switch is closed, then effectively it's not there, and then ground. Okay, so you know that when this capacitor has a chance to charge up, you know that if that's 9 volts there, then that is going to be 9 volts as well. And you know that if there's no flow of current going through this resistor, because basically, how can you have flow of current going through there when this switch is open. Okay, you'll have a transitory current while the plate is charging up perhaps, but it won't be a continuous current after that. So with no flow of current, then you won't have a voltage drop. So if that is 9 volts, just like I was saying earlier in the call it a lesson video, okay, then there's no current flowing through there, so there's also no voltage drop. So basically we've got 9 volts on either side. So in other words, we've got 9 volts on that side of the capacitor, and we've got 9 volts on that side of the capacitor. Now, if you're one of my A-level students and you've done high power switching systems, you might now guess what's actually going to happen next when we press the switch. If you're a GCSE student, I'd say it's probably pretty unlikely that you're actually going to guess what's going to happen. So when I press the switch, you can hopefully see that, well, let's just have a look at, I think it was this one. When we press the switch, it takes the voltage immediately down to 0. So it either is 9 volts or it's 0 volts. Okay, 9 volts up here, 0 volts down there, and you know, nothing in between. But when we press the switch here, yes, it is going to go down to 0 volts. Okay. So it's going to this side of the capacitor is going to go to 0 volts because this side is going to go to 0 volts. Okay, so that is all as you would expect. However, and this is the thing that you might not expect, however, you can't have an immediate change in voltage across the capacitor. And that's something you're probably not going to know about if you do GCSE electronics. And because you can't have an immediate change in the voltage, then you know, the potential difference between those plates, this is going to also be taken to 0 volts. Now, I think that's would be a good point when we actually run this as part of the simulation. Okay, so let's just have a look at this. Okay, first of all, let's just look at this side and just confirm that when we press that, before we press the switch, that's going to be 9 volts, and then when we press the switch, it will be immediately 0 volts, as good as immediately. Okay, so let's just run this. Okay, so initially 9 volts, and when I press the switch, it goes down to 0 volts. Hopefully you can see at the bottom of the trace there's a little red line going along, and then when I release, then it goes up. Now, it did take a little while to go up because of the charging of the capacitor. Okay, don't worry about that too much at the moment. On the other side, so let's just stop the simulation. Let's now just run the simulation again. On the other side, we've got 9 volts. Just like I said before, we've basically just got a resistor and capacitor. Okay, so that is going to be, and there's no flow of current. There can't be any flow of current because if you look, there's no route going from the supply down to 0 volts because look, you know, the switch is open. But when we then press the switch, remember this side is 9 volts, this side is 9 volts. When we press the switch, even though the switch is connected on this side and not on this side, when we press that switch, you'll notice that it momentarily went down to a low voltage. Didn't quite go down to 0 volts, but it, you know, got down to what, 2 volts or something. And 2 volts is less than 1/3 of the supply voltage, which is 9 volts in this case. So, and I've still got my finger on the switch, and then you'll notice that it recovered. So let me just quickly do that again. Don't worry about that blip. We're going to talk about that in a bit. But when I press the switch, it goes down briefly to a low voltage, and then it recovers. And then when I release the switch, then this overshoot thing happens here, which we'll talk about in a bit. So the reason for it acting like that is, in fact, let me just quickly take another screenshot. Okay, so let's get rid of that. And I'm sure some people, some YouTubers have loads of good software to do this. I'm just making do. Not professional. There we go. Okay, so when the switch is closed, okay, so let's just close that switch. So when that switch is closed, remember then we can then have this charge. This is going to charge up to 9 volts. Okay, it charges up to 9 volts. There will be a flow of charge through this resistor until it's charged 9 volts, and then it stops, and this side will be 0 volts. Okay, when you press that switch. Now, hopefully that's making some sense. So initially it changes to, remember it initially, because you can't have the difference, the immediate change in difference in potential across the two plates, they both fall to 0 volts, and then this side will quickly, it depends on the size of the resistor, of course, it will quickly recover to this supply voltage of 9 volts. So it's only transitory, okay? It's only temporary, the dip in the voltage on this side, and I've labelled this output, but that would actually be the trigger input to the 555 timer. But if we just go back to the simulation, you'll notice that there's this thing happening here, this let's call it an overshoot, okay? And actually, if we fit to data, you'll actually see that it jumped up to 15 volts, okay? So that's actually probably going to be a little bit unexpected, particularly because we've got 9 volt supply. Now, we're not going to do any calculations in this video. Maybe I could do that in another video. But you might start to wonder, well, why did it overshoot? Okay, so let's take another screenshot, and I'll paste it in here. Let's go scroll on down. Okay, so we went to, if you remember, we went down to, let's just change it to that. Okay, so we went down to 0 volts. Okay, if you remember that, we went down to 0 volts, and then this side was 9 volts. Okay, and then we then released the switch. Okay, so when you release the switch, then what's going to happen? Okay, that's the question, isn't it? What's going to happen then? So when you release the switch, then that's going to go to 9 volts. Now remember, there was a difference previously. There was a difference between these, a difference of 9 volts. Now you can't have an immediate change in the voltage across the plates, so that means when this side goes to 9 volts, the difference is going to have to stay the same. Now, if the difference between 0 and 9 was 9, the difference between 9 and this side is now going to have to be that this side goes to about 18 volts. Okay, it isn't exactly 18 volts, but as you saw in the simulation doesn't show that it's 18 volts. But hopefully you understand the principle that you can't have an immediate change in the potential difference across that capacitor. So that might be a bit of a problem to you, because now you've got the output does the low, which we wanted to go to trigger, but maybe you don't want it to then shoot up. Might not be a problem to you, but you can counter that quite easily, because what you can do, you can clamp that voltage. So what you can do, you can just stick a diode here. Okay. So what I'm doing here now, remember that this side of the capacitor went to high-ish voltage, that's 15 volts, 18 volts, something like that, which is greater than the 9 volts. So this has a greater potential than this side, so then current can flow through this way. Now, of course, if we've got a diode here, then there can only be a diode's worth of potential difference between these two, between this, the output, and this supply rail. In other words, we can only, if it's a silicon diode, only 0.7 volts difference, which means that this output now can only be up to 0.7 volts higher than 9 volts, in other words 9.7 volts. So if with this modified circuit, now if we run this simulation and we press the key, we'll have that momentary drop in the output, and then it will quickly recover like that. And then when I release the switch, now you've only got a very small blip of probably something like about, well, no more than 0.7 volts above the 9 volts. Okay. Now, hopefully that makes some sense to you. Now let's have a look at my putting all that together. Okay, so what have we got here? Well, we've got the initial basic pull-up resistor on the and the switch, okay, and then we've got that capacitor, and then we've got this side, the resistor on this side. And by the way, I didn't actually do any calculations, could do some calculations, but it's probably unnecessary. And then I clamp that overshoot using the reverse bias diode there, okay. And that's it, okay. So let's just run the simulation. And so the what do we? Let's monitor the output for the moment. So that's low at the moment because LED's off, okay. And I'm just going to press the switch briefly. And you'll notice then it goes, for whatever timing period is. I think that looks like 1.1 second. And then this time around, I'm going to press and hold the switch. But even though I've still got my finger on the switch, it doesn't make any difference to the timing. And that's really useful because now if we were to go for a very brief timing period, let's say, doesn't really matter, does it? Let's say, let's go at 10 microfarads. Okay, this is going to be very quick. And it would be impossible for me to press and release this key in sufficiently short time to not affect the output time. That if I press this, you see that we have that tiny momentary, and even if I press and hold it, it makes no difference. Okay. Right, I hope that's useful. Like I say, for the typical GCSE or A-level project, when you're using one of these timing chips, the 555 timer, if you've got like a long output duration and you can rely on the user not pressing the trigger switch for too long or longer than the output you were expecting, then you don't have to do any of this stuff. But every year I would say that there's probably going to be a student or two who actually maybe wants to do something like this in their project. So hope that's useful, and please thumbs up, and feel free to leave comments if you found it useful. Thanks very much, and goodbye.